Acids and bases, factors that influence acid strength. Part A, we're going to be talking specifically about electronegativity. Now, electronegativity is a concept that we talk about in general chemistry, and this is the tendency of an atom to pull electrons towards itself. Therefore, the more electronegative an atom is, then the more polarized its bond with hydrogen is, and the easier it is for that hydrogen to pop right off. Therefore, the stronger acid has the higher electronegativity. And what we're doing in this particular problem is comparing pairs of acids. So because oxygen has more electronegativity than nitrogen, it has the stronger acid. Similarly, fluorine is the strongest acid in this pair because fluorine is the most electronegative atom. So in these cases, we have our stronger and weaker acid. Now oxygen is more electronegative, there we are, than nitrogen. Therefore, that's going to be the stronger acid. Part B, we're looking at hybridization state. Now this also has to do with electronegativity. So the stronger acid is going to be the least hybridized. So what we have here is an sp3 carbon, and what we have here is an sp2. Therefore, this is going to be a stronger acid than this because the sp3 is less electronegative than an sp2. So working on those hybridization electronegativities, we have the more bonds it has, then the less hybridized the orbitals are, the stronger the acid. Now in this case, we have sp2 and sp3. The sp3 is going to be a weaker acid than sp2. And in here, we have an sp versus sp2. Now in part C, we're looking at atomic size. The stronger acid will be the one that has the larger atom. So fluorine is a smaller atom than bromine. Remember your periodic trends. Therefore, it will be a weaker acid than hydrogen bromide or hydrobromic acid. Now, chlorine is smaller than iodine. Therefore, it's a weaker acid. The larger the atom, the stronger the acid. So oxygen is smaller than sulfur, and nitrogen is smaller than phosphorus. Part D, we're looking at inductive and resonance effects. So what you need to consider in this particular problem is that the electronegative atom, so in this case we have an additional chlorine, is going to pull electrons towards itself. And when it pulls the electrons towards itself, it decreases the amount of charge that's on the conjugate base, and that stabilizes the base. Therefore, the more stable the base, the stronger the acid. Similarly here, these fluorines are closer to the acidic hydrogen. Therefore, this is a stronger acid, and this is a weaker acid when comparing these two, because all of the electronegativity of these fluorines pulls on all of these electrons in order to create this oxygen. Makes a very good leaving group at that point. He'll pop off, and then this becomes a very stable base. So similarly, this is stronger than this one because it has two fluorines rather than one, and in this case 2 fluorines are greater than 2 chlorines. Therefore, the 2 fluorines lead to the stronger acid. Basicity of amines, we're specifically looking at ammonia. So which side of the equilibrium shown in the following figure is favored? So are we favoring reactants or products? So the answer lies in the pKa value. Now I looked up the pKa values in Appendix 1 of your book, so I'm looking at page A1. And on page A1, the pKa of ethanoate is given as 4.8. So we have 4.8 over here on the reactant side. Now I know this is acting as the acid because on the product side it's lost a hydrogen. Now this over here, the ammonium ion, is the acid on the product side, and it has a value of 9.4. Therefore, the equilibrium will point towards the larger pKa value, therefore it will favor products.